Welcome to the course on advanced machining processes. Today I am going to talk about abrasive jet machining. Organization of today's lecture is as follows: introduction and working principle of abrasive jet machining, experimental setup used for abrasive jet machining, mathematical models for material removal rate in abrasive jet machining, parametric analysis of abrasive jet machining, process capabilities of abrasive jet machining process, some solved examples and question bank that is to be given. Let us start with the introduction and working principle of abrasive jet machining process. Now, mechanical type of advanced machining processes, as we discussed in the classification in the last lecture, it is mechanical type where we have abrasive jet machining, ultrasonic machining, water jet machining and abrasive water jet machining. These are the various types of machining processes which come in the category of mechanical type of advanced machining processes. Then there are the finishing processes with the help of which we can achieve micro or nano level surface roughness value, that is the RA value in these processes. First one is abrasive flow finishing process or also known as abrasive flow machining process. Second one, magnetic abrasive finishing process, chemomechanical polishing CMP. Next is magnetorheological finishing or also called as MRF process, and magnetic float polishing. We will discuss most of these processes in this particular course. Introduction to all these processes will be given in this course. Now, let us see this very interesting picture. There are two persons throwing a ball on the wall, and see, first one is applying the force F1 and it is penetrating to a certain depth and the diameter is D1. Second person is throwing with a force F2 and it is penetrating to a deeper depth, and you can see here that force F2 is greater than the depth to which it is penetrating. As you can see here, H2 is larger than the depth for which it is penetrating in case of the force F1. So, this will depend upon how much, with what velocity the person 1 is throwing the ball and the person 2 is throwing the ball. In second case, the velocity or the force being applied on the ball is larger than the first one, and that is why H2 is greater than the H1. Now, in the second case, the kinetic energy of the ball is larger than the first case, that is why depth of penetration H2 is larger than the case of H1. Same way we will see that thousands of abrasive particles that are hitting the workpiece, they are removing the material, smaller material or more amount of material depending upon with what kinetic velocity, kinetic energy they hit the workpiece surface. Now, let us see how abrasive jet machining or AJM works, which is the more or less the same as we discussed in the earlier slide. Here you can see, here is a nozzle through which a mixture of air and abrasive particles is coming out. In place of air, you can have some other gas also. Now, here you can see the distance between the tip of the nozzle and the workpiece surface, where it is hitting the workpiece surface or abrasive particles are hitting the workpiece surface, that distance is known as nozzle tip distance, NTD, or it is also known as standoff distance, SOD. Normally it is written as SOD. Now, this air and abrasive particle mixture consists very fine abrasive particles, and you can see here this is the workpiece